Chapter 4 is the last chapter to cover in this class, Computer Organization 1. The rest of the chapters will be covered in Computer Organization 2 class. So what we have done so far through chapter 3 is as follows. In chapter 1 we didn't teach, however it just gives a brief overview of computer systems. In chapter 2 we learned how data are stored and manipulated and then represented. In chapter 3 we studied the fundamental components of digital circuits, combinational circuit and the sequential circuits. Having all this background, now we are ready to understand how computer components work, how they fit together to create computers. So first component that we are going to study in computer system is a CPU. CPU acronym for Central Processing Unit. That's the heart and brain of the computer. What it basically does is it fetches instructions and decodes, understand what instruction is, and then it executes the instruction. So that is called the program execution cycle, and the CPU continues to do so as long as there is a program to execute. Within the CPU, inside the CPU, we can think of two parts called the data path and the control unit. So data path consists of arithmetic and logic unit, which does all those operations like AND operation, OR operation, or addition operation, subtraction operation, or comparison, and those ones. Any arithmetic and logic operation is done by the arithmetic logic unit, which is called the ALU, and then it has storages within CPU. The storage within CPUs are called registers. You can consider it as a D flip-flops, a group of D flip-flops. So they are interconnected by bus. Then also it's eventually connected outside the CPU to main memory. So that's the data path part. So data and the path part. Another component in CPU is a control unit. So control units is to perform sequenced operations according to the signals provided. So we have two parts in CPU. The registers hold the data that's already accessed by the CPU. So register is a special memory within the CPU, which is inside the CPU, and that is called registers. And then the speed of the registers is very fast, okay, as fast as the whole CPU works. Compared to main memory is slower compared to CPU. So that's why we have some special very high speed memory within the CPU to take care of some of the things that needs to be taken care very fast. And then you can imagine those registers as a group of D flip-flops. We learned in earlier study that using flip-flop we can represent the 1-bit memory. So if you want to have a 1 byte of memory, you have 8 flip-flops using in parallel, then it becomes an 8-bit memory. And then if you need a 32-bit, then you need to have a 32 D flip-flops in parallel together. So arithmetic and logic unit carries out any logical operation, comparison, and, or, and the like, and arithmetic operation, addition, subtraction, and then some advanced CPUs could do more than those addition and subtraction though. And all of those are directed by control unit. So control unit determines which actions to carry out. So using those registers and the like. That's what's happening inside the CPU. And then the bus is to share information between two components. So CPU shares data with other systems by the way of a bus. So a bus is physically a set of wires that simultaneously convey a bit of information from one component to another, and each line carries one single bit information, 1 or 0. And then we can think of two types of buses. So point-to-point bus or multi-point bus. Point-to-point bus is between two components. You have a dedicated set of lines connected together. That is called a point-to-point. Suppose we have a component called the serial port, another component called the modem, and there is a dedicated set of wires connected together, and that is called the point-to-point bus. So another component, for example, ALU, and then control unit, if we have a dedicated, not shared by any other component, then it is called the point-to-point buses. So in a typical bus, it consists of a set of wires, a set of lines. Some of them are for data, some of them are for control, and some of them are for address, depending on what two components are being connected. So data line, as its name implies, it conveys the information, data information from one to another. The control line determines the direction of a data flow from A to B or B to A. These are the control lines. And then there is some other line called the address line. Address line determines exactly where inside A or B you are referring to. Suppose this one is a memory, this one is some CPU, then address line determines uh, which memory address you want to store data or retrieve data. So that's address lines. So in a picture representation, suppose we have a bus connecting CPU and main memory, then address line is to select which memory at address what you want to read or write. A data line is if you want to write, the actual data is on data lines. If you read the actual data from memory is presented on data lines. And control lines is this read or write. That's the direction of the data flow. So that's a typical structure of buses. The multi-point bus is something like that. One bus is shared by many components, not having dedicated ones. So that's a multi-point bus. In multi-point bus, then we need something called arbitration. Arbitration is suppose the CPU wants to use the bus to store data into the memory, while the disk controller needs to store some data inside the memory into hard disk. Then we have some conflicts, so the use of a bus should be arbitrated, and there is some arbitration protocol within the bus. We have many different simple ones and complex ones and so on. So in master-slave configuration where more than one device could be the bus master, then we should have some arbitration protocol implemented. And then another component in computer system is clocks. So clocks, every computer should have a clock because all the activity events are synchronized with a clock. So clock frequency is the very bare form of computer performance, but that's not all. Some details we need to consider, which I will discuss in next slide though. But the very apparent thing is how fast the computer is clock frequency. So we typically use 1 gigahertz CPU or 2.2 gigahertz and the like. And megahertz is in these days too slow for a CPU clock though, but some part of the computer system we use some megahertz range, and some part of the computer system, especially inside the CPU, we use some gigahertz clock and so on. So clock cycle time is inverse of the clock frequency. Means that clock frequency means in 1 second there is 800 mega ticks happens. So then it's something like this. So within 1 second, you have 800 millions of those clock ticks are there. Then what is the time for each clock tick? That is cycle time. So what you do is just take inverse of that. That becomes the value of the second for one clock tick. That is 1 over 800 million. That becomes 1.25 times 10 to the minus 9 is there, which is a nanosecond. So 1.25 nanosecond is a clock cycle time if a clock frequency is 800 megahertz. So clock speed is somewhat related with the CPU performance, but CPU performance is determined or defined differently. The CPU performance or CPU time is how long does it take to run a program. So we divide it by that. So the number of seconds it took in the per program, that is called the CPU time. But this equation could be expanded. Program means a number of instructions per program, and then per instruction there's average cycles there, and then per every cycle how many seconds it took. So if we expand it that way by mathematical formula, we can verify that, since we can cancel this one, same thing out, this cycle and cycle same thing out, then remaining is a seconds over program, the same thing. But in detail, we can think of three components when we define CPU time. So to have a better computer performance, which means to reduce the CPU time, then program ends quickly, completes quickly, then what can we do is the first thing is here. Per program, we can reduce the number of instructions. Then this number will be reduced. So reduce the number of instructions in the program. Second one is per instruction, let's reduce the number of cycles. So reduce the number of cycles per instruction. Third one is per cycle, let's reduce the number of seconds and make the cycle shorter. So reduce the number of seconds per clock cycle. So we can focus on three things to enhance the computer performance in terms of CPU time. So for this part, we can make the clock as fast as we can. That's the third part. If you have 1 gigahertz CPU rather than 2 gigahertz CPU, then 2 gigahertz CPU has a smaller value here. But number of instructions per program does not affected by clock speed of the CPU. And this one is what compiler does. Compiler produces less number of instructions. It's more optimized code, then performance is enhanced. And the like, and then per instruction number of cycles. That's how CPU is designed. So if you design a better way of a CPU that takes less cycles per instruction, then CPU performance is enhanced. Some of those aspects we are going to study in Computer Organization 2 in next advanced course. And then in a computer system, there is an input and output. Here, input and output means the one who communicate outside the computer system. So we have a computer system, then computer system should communicate outside output and input. For example, keyboard. Keyboard is a human interface to read from outside to inside the computer system. So keyboard is an example of input, and then you have a screen, monitor, display, then that is a output system in computer system. In I/O system like a keyboard, a monitor, a mouse, and so on, in a computer system, we have two ways of providing I/O system. One is called the memory mapped, the other is called the instruction based. So memory mapped means that there is no distinction between memory and I/O devices. So if you write certain address, for example 100, then this means memory, for example. Then if you write at address 2000, that means a monitor screen. So we do same write operation, but depending on the address range, some case it means a memory, some case it means a monitor screen, and so on. That's called a memory mapped I/O. But instruction based one is that to write into memory and to display on the display on a monitor screen or memory is two different instructions are there. So for example, write to memory or write on display, something like that. So we have separate instructions depending on whether it's a input-output system or not. Then that is called the instruction-based I/O system. So one last thing before we study memory organization, which is quite complex. In computer system, there is something called the interrupts. In normal execution of a program by CPU within the computer system is a fetch, read instruction, understand it, decode, and then run it, execute. That is a program execution cycle. But something happens, then this cycle is interrupted. That is called the interrupt mechanism. So CPU is alerted to such an event through interrupts. Interrupts can be triggered by I/O request, or some error occurs, or some invalid instructions encountered, and so on. For example, when you run the program, if you click the mouse button, mouse on some button, so we have some program running, and here is a OK button or submit button, and so on. As you click the button, then interrupt is generated, and then it interrupts the normal CPU program execution cycle, so that CPU can respond to your button click and the like. So that's the some brief idea of what interrupt happens and what's happening inside the CPU. So each interrupt is associated with a procedure that directs the action of the CPU when interrupts occurs. When a keyboard is pressed, when mouse is pressed, and the like, then we can associate certain action to those interrupts. So that is handled within the CPU. That's another system, subsystem within computing systems.